Hello and welcome everybody to our IROS workshop presentation, which has the title Software Quality as a Key Requirement for Safe and Secure Robot Applications. My name is Michael Rathmair and my colleague who is also presenting is Benjamin Breiling. We are both affiliated with Joanneum Research Robotics, which is a research company located in Klagenfurt, Austria. We are both working in the research group Robot Systems Technologies. So first, let me give a short introduction and let's motivate the key factors of our talk. Modern robot systems include a lot of software components which are responsible for key features as sensing, reasoning, information management and also acting. So if we want to ensure safe and secure robot applications, we also have to ensure that these software components have safety and security properties. So this is the key factor of our talk. We want to focus in this software quality properties and we want to give some best practices and we want to discuss some methods how to evaluate, ensure and also to enhance software quality in your robot system application. So if we talk about security and especially safety of robot applications, a lot of standards and legislative documents appear. Nevertheless, the highest directive available is the EU Machinery Directive, which gives the legislative framework of the safety and security of robot applications. On the second level, we have a rich set of standards. For example, for functional safety requirements, we have the ISO 13849, which is about the performance and also the requirements, functional requirements of safety-related robot system parts. So this standard is in revision, and this year this standard is published in the DIS status, so in the Draft International Standard status. Another part is security. We also have a standard in place for security properties, which is the IEC 62443, which also includes a part about security in the automation domain. Last but not least, and luckily we have a lot of Type C standards, so specific standards for robot applications, and the most prominent one is the ISO 10218 standard, which has two parts. So part one is for the robot safety itself, and part two is about the safety of the robot system. Both parts are in also in revision, and there is a draft international standard status version available in the ISO portal. Last but not least, we also have several standards for mobile robots and also for mobile manipulation. For example, the ISO 3691, which is also a Type C standard and published in the latest revision in 2020. So as you can see, we have a lot of requirements for robot system applications, which also include software requirements and functional software requirements.
Next, I want to talk about safety and security of robot systems. In our case, the Chimera robot, consisting of a serial manipulator and a mobile base. If you look at the two robots separately in terms of safety, the mobile base has a built-in PLC which is able to stop the robot in order to avoid collisions with human and objects. The manipulator has a safety installation for for example, for limiting the momentum occurring at the end effector. In terms of security, we have a Wi-Fi interface and the PLC, which are secured with standard passwords. Further on the manipulator, we have a controller running Linux OS and with standard username and password, and also the remote interfaces are not secured. Next, I want to show how the security flaws presented on the previous slide can lead to serious safety threats. In order to demonstrate that, we modified the program on the safety PLC, which is responsible for stopping the mobile base in case a collision with a human or an object is about to occur. Since the Wi-Fi interface and the PLC are weakly secured by standard passwords, it was no problem for us to access the PLC and modify the program. As a result, the PLC didn't stop the robot despite laser scanners detected an object in the way of the robot, which causes a collision with this object while driving with full speed. As a consequence, we decided to build our own network architecture around the existing one, and so encapsulated the PLC and the low-level robot control from the outside world, and provide a single access point for our robot, which is also secured by standard security measures. In the next part of our presentation, we want to focus on software quality. First, I want to describe the continuous integration and deployment process we use in order to initially deploy or update a program on a robot system. Our continuous integration and deployment process consists of 3 stages. In the first stage, we check if our program is syntactically correct. So this is also dependent on the program language we use to develop our program. In the second stage, we test and verify the program so that we can also be sure that it behaves correctly in terms of requirements coming from the application, but also coming from safety and security. And in the last stage, the release stage, we add a version to the program and generate a signature. And with this signature, the robot system can check if the continuous integration and deployment process was successful, and only if this is the case, the program is executed on the robot system.
So thank you, Benjamin, for this nice introduction about software quality requirements and the associated test methods in order to achieve these requirements. Now I would like to focus a little bit more into verification and validation of software, and especially in the structured test of software features. Therefore, I have chosen a small example as illustrated here on the left side of this slide. You can see a robot which can be enabled or disabled. but the robot is just enabled if the blue zone and the red zone indicated by the variable a and b are not occupied, so they are set to 1. Another method to enable a robot arm is whether the zone A is not occupied and the user presses an enabling device which is indicated by a true signal of the variable C. So this feature can be implemented in a piece of software as indicated here in this gray box, and the software is a set of if-else branches and associated instructions setting the robot enable signal, which is Y, to true or false. Another method to illustrate that function is a logic gate array, as you will implement it into a safety PLC. So the task to achieve in this small example is to design a test case checking the following functional requirement. The robot is just enabled if the zones A and B are not occupied. So we are verifying the feature of the zone enabling, the zone-based enabling of the robot device. Therefore, we define two functions, the function f, which is indicated by the logical formula and gives the correct function of the robot system, and the function f alpha, which indicates that also if the zones A and B are not occupied, also the robot is not enabled. So this is the faulty function. In order to achieve a test case for this software feature, we do an XOR operation with the functions f and the functions f alpha, and then we get a logical formula, and we assume that the output of this XOR function is 1, so that the faulty and the correct feature is not equal. And if we solve this logical formula by a satisfiability solver, we get out a solution for the test case T alpha, and we can get as a result that if we we set the variables A to 1, B to 1 and C to 0, and if then T alpha is 1, then we get a faulty system, and we get a test case which checks especially this functional requirement. So on this slide I brought another example which is located on a higher level of abstraction. And in this example we use the approach of formal model checking, which proves that a specific property is satisfied within the software you implemented. So as you can see, there is a workflow given about a robot which grips a workpiece, and the gripping process itself can be successfully or unsuccessfully. And if it is successfully, the robot moves to a place position, and if the gripping process fails, the robot takes an error state. And as you can see on the left side here, this workflow is implemented as an BPMN based model. And on the right side you can see that this BPMN functionality is translated into a transition model, which is directly handed over to our formal verification tool. So as a second input, we need the property to be verified, and therefore we defined a specific verification goal. And the verification goal in natural language is that it has to be verified if it is possible that the robot reaches the error state after the gripper is closed successfully. So this function, this property, must not be implemented in our software. So, because if the gripper is closed successfully, the robot must reach the move to place position and not the error position. And especially this feature is formulated as a property, formal property formulation as given on the lower side of this slide, and this is the second input of the formal verification process. So then the property formulation and the formal model is computed, and as a result we see that it is not possible that if the gripping is successfully, the robot does never end up in the error state.
Finally, I want to give a brief summary of our presentation. We showed how the three aspects, safety, security, and software quality, are interrelated by introducing a continuous integration process, focusing especially on the test and verification phase, where we show how a robotic program can be formally verified and validated in order to ensure the functional safety of our program and that also security requirements are met. With that, I want to end our presentation and thank you for your attention.